Roman concrete, also called opus caementicium, was a material used in construction during the late Roman Republic through the whole history of the Roman Empire. Roman concrete was based on a hydraulic setting cement. Recently, it has been found that it materially differs in several ways to modern Portland cement. It is widely acknowledged that Roman concrete is the most durable type of cement of its kind due to its use of volcanic ash. By the middle of the 1st century, the material was used frequently as brick-faced concrete. Although variations in aggregate allowed different arrangements of materials, further innovative developments in the material, called the Concrete Revolution, contributed to structurally complicated forms, such as the Pantheon dome, the world's largest unreinforced concrete dome. Roman concrete was also used to make roads. Material properties. Roman concrete, like any concrete, consists of an aggregate and hydraulic mortar, a binder mixed with water that hardens over time. The aggregate varied, and included pieces of rock, ceramic tile, and brick rubble from the remains of previously demolished buildings. Reinforcing elements, such as steel rebar, were not used. Gypsum and lime were used as binders. Volcanic dusts, called pozzolana or pit sand, were favored where they could be obtained. Pozzolana makes the concrete more resistant to salt water than modern-day concrete. The pozzolanic mortar used had a high content of alumina and silica. Concrete, and in particular, the hydraulic mortar responsible for its cohesion, was a type of structural ceramic whose utility derived largely from its rheological plasticity in the paste state. The setting and hardening of hydraulic cements derived from hydration of materials and the subsequent chemical and physical interaction of these hydration products. This differed from the setting of slaked-lime mortars, the most common cements of the pre-Roman world. Once set, Roman concrete exhibited little plasticity, although it retained some resistance to tensile stresses. The setting of pozzolanic cements has much in common with setting of their modern counterpart, Portland cement. The high silica composition of Roman pozzolana cements is very close to that of modern cement, to which blast furnace slag, fly ash, or silica fume have been added. Compressive strengths for modern Portland cements are typically at the 50 megapascals level and have improved almost tenfold since 1860. There are no comparable mechanical data for ancient mortars, although some information about tensile strength may be inferred from the cracking of Roman concrete domes. These tensile strengths vary substantially from the water-cement ratio used in the initial mix. At present, there is no way of ascertaining what water-cement ratios the Romans used, nor are there extensive data for the effects of this ratio on the strengths of pozzolanic cements. Seismic technology. For an environment is prone to earthquakes is the Italian peninsula. Interruptions and internal constructions within walls and domes created discontinuities in the concrete mass. Portions of the building could then shift slightly when there was movement of the earth to accommodate such stresses, enhancing the overall strength of the structure. It was in this sense that bricks and concrete were flexible. It may have been precisely for this reason that, although many buildings sustained serious cracking from a variety of causes, they continue to stand to this day. Another technology used to improve the strength and stability of concrete was its gradation in domes. One example included the Pantheon, where the aggregate of the upper dome region consisted of alternating layers of light tuff and pumice, giving the concrete a density of 1,350 kilograms per cubic meter. The foundation of the structure used travertine as an aggregate, having a much higher density of 2,200 kilograms per cubic meter, used by other ancients. In the Philippines, large monuments and burial tombs were constructed using limestone blocks. They were cemented together with a form of ancient cement. After completing a structure or sculpture, the entire work was coated. Within Taban cave, sculptures of elephants may have been made in the same manner. Research to answer questions this raises will be conducted at a new college in Palawan. Modern use. Recent scientific breakthroughs examining Roman concrete are gathering media and industry attention. Because of its usual durability, longevity and lessened environmental footprint, corporations and municipalities are starting to explore the use of Roman-style concrete in North America, substituting the volcanic ash with coal fly ash that has similar properties. Proponents claim that concrete made with fly ash can save up to 60% of the cost because of less aggregate use, lessen the environmental footprint by having a lower cooking temperature, with a much longer lifespan. Usable examples of Roman concrete exposed to harsh marine environments have been found to be 2,000 years old with little or no wear. Literature. Jean-Pierre Adam, Anthony Matthews, Roman Building, 1994. Lynn C. Lancaster, Concrete Vaulted Construction in Imperial Rome, Cambridge University Press, 2005. Heather N. Legtman and Lynn W. Hobbs, Roman Concrete and the Roman Architectural Revolution, Ceramics and Civilization, Volume 3. High Technology Ceramics. Past, Present, Future, edited by W. D. Kingery and published by the American Ceramics Society, 1986. W. L. MacDonald, The Architecture of the Roman Empire, Rev. ed. Yale University Press, New Haven, 1982.